flow simulation, and we'll look at different examples of, or should I say, problems that you might encounter in your design process, and where flow simulation will, of course, help you with in solving these problems, or at least just better understand your models. So let's start with the first example, which will be quite simple, but at least it'll illustrate the different capabilities of the software. So we'll start with a ball valve example, and first of all, I'd like to just go over the flow simulation interface. If you're already familiar with SolidWorks, and well, you probably know the types of layout for the different types of features we have in SolidWorks using tabs. Well, by adding the flow simulation add-in, you will face the similar tab with, of course, flow simulation features only. And all the features are available through that tab, of course. Also, you'll have a pull-down menu available, once again, to have access to specific type of features or specific functions if needed. All right, so to start the analysis here, we usually create the analysis by using the wizard, which is a kind of an assistant, if I can say, that will help you to make sure that all the necessary properties are inserted into the software. So first, I'll just give a default name to my analysis, in this case flow test 1, for example. The next step will be selecting what types of units we'd like to use, or a unit combination we'd like to use. For example, if instead of using Kelvin as the default unit for temperature, I'd like to use, for example, Celsius or Fahrenheit. So you'll be able, of course, to edit any kind of unit you'd like. Let's say I'd like to have my length unit in millimeters instead. So this is, of course, for starting with the default international system units. Of course, predefined English unit system is, of course, available also. So you have this type of functionality for where you can select different types of units for basically any type of units available in the software. So everything's there, and you can, of course, personalize all these units. The second step is basically selecting what type of environment you'll be working in. In this case, we're mostly concerned about what's happening, of course, inside the ball valve with the flow going through it. So we'll, of course, pick the internal analysis option. If we would be interested in what's happening outside the ball valve, let's say there's an outer flow going around it, then, of course, the external option will be of interest in this case. So I'll pick the internal. Like you see here, there's a few physical features available. Let's say we want to consider heat conduction in solid, so we'd of course check that. Radiation, same thing. We can do transient analysis or time-dependent analysis. So we'll pick, in this case, the duration of the analysis and the time step of the analysis. Also, we'll pick gravity in some cases, for example, to consider natural convection. So gravity will be interesting for these situations. Rotation as well is available, so we can define rotating regions to simulate impellers, for example, and of course evaluate how the flow will behave consequently. In our case here, we will not need any of these physical features, so we'll just keep the default as it is. We keep going, of course, with the fluid selection. In this case, there's different types of fluid available by default in software. So air, of course, is one of them, since it's probably one of the most used fluid. Also, under liquids, we'll find water as well, which is what we'll use in this case. Note that we can have access to non-Newtonian liquids, compressible liquids, real gases, and, of course, steam, which is water vapor. Under flow type, we can select laminar or turbulent. Most of the cases we'll pick both of them, but if you know you're in a laminar or turbulent environment only, you can of course pick these options. Cavitation is available for water and industrial liquid as well. And note also that we can create a simulation with up to 10 fluids mixed up in the same simulation. In this case, we'll keep the default boundary conditions, outer wall conditions, I should say. We'll use a default roughness of 0 micrometer, but if roughness is a concern for your analysis, you can of course insert different values than the one by default. The last, or should I say one of the last panel is the default environment condition. In this case, it'll be the environment pressure and environment temperature. So we'll just keep them as default, which is about 72 Fahrenheit or 20 C. The meshing now, in this case, we want to set the level of resolution for the calculation. A level of 1 will lead into a fast calculation, but the results might not be as precise as we wished. So, and on the other hand, if I push this little slider to the far right at level 8, then I might encounter a very, very long solution time, but much more precise result. So it's always a give and take situation. In this case, normally we start at around 3 and refine the resolution level if needed a little further in the process. So I'll just click finish here. And once we're done, you can see that a new tab just appeared here. This is the flow simulation tab, completely integrated into SolidWorks, and we'll complete the definition of our study with this tab. Before going on, I just want to, for example, use these two, put these two parts transparent so I can see inside the geometry. I can probably just take a section view to better show exactly what we will solve. We just have a ball valve at a certain angle. Flow will come in this side, come out this side, of course, and we want to see how the flow will behave under this angle of the ball valve. So, first step will be, of course, defining exactly what will be the input. In this case, we'll use a boundary condition feature to define the input. So if I go under inlet volume flow, for example, I'd like to insert, I don't know, maybe 0.05 meter cube per second. Clicking OK. And we have our flow condition established. The second one will be regarding the outlet of the system, of course. And in this case, we'll define a pressure value of environment pressure with the environmental value and ambient temperature of 20 C again. The last step in this case before launching the calculation will be defining what we call goals, or we can call them also sensors. Let's say we'd like to follow what's happening regarding velocity in our system. So I'd like to follow the average velocity of my system, and also we know the output pressure, we know the input volume flow, but what will be the pressure at inlet? We don't know. So the software will tell us that. And I'd like to follow that value, so I'll insert here another sensor that will allow me to follow the average static pressure at inlet. So we could define much more sensors like that to follow any type of results during the calculation and make sure that these results reaches a certain level of stability before stopping the calculation. So that's also the goal of these goals or sensors. And so from here, I'm ready to click Run and launch this. So a solver window will show up, and it will show us basically the evolution of the calculation. Now it's completing the mesh, and the calculation should start anytime soon. And what's very interesting is that we can follow the sensor's value we just created. So during the calculation evolution, we can follow how the velocity and the pressure are varying. And in this case, we can see the last value. So we have a pretty high speed, and pressure variation here stabilized as well over time. So once we're done, we can now look at the results. And looking at the results, there's a lot of different tools or options we can use. First of all, the cut plot is probably one of the most common one, where we'll just take a slice of our analysis domain basically and look at this. Now we're looking at the pressure distribution from the inlet side to the outlet side. I can add up, of course, a lot of colors to better see the distribution of the colors, and look at the pressure distribution. So there's a pressure build-up on this side, and of course we have environmental pressure at the far end. Also, I can look at, for example, the velocity value, and we have a maximum velocity actually that's fairly high. So we have above, in this case, we have a value that's far above speed of sound for water, I guess. So this is, or probably not, since we had no warning during the calculation. But anyway, we can clearly see the speed profile established into the valve in this case. So this is just a question of my volume flow that was probably too high. That's why we are getting so high values. We can also look at it in a different profile. So let's say I'm changing my plane here and picking plane number 2. So I can now look from the top at the speed distribution. So we can clearly see that the speed is increasing when it gets through the ball valve, and after that it tends to, of course, decrease in speed. Another very interesting plot type is actually the flow trajectories. So I will, in this case, just pick the inlet face and show me 20 trajectories of flow. And I'd like to use, for example, 3D arrows. So I'm just saying OK to this, and I can clearly see exactly how my flow will behave. And not only that, I can, of course, animate this to see exactly what's happening in 3D. So a very, very convenient way of looking at your results is using flow trajectories. I'll just now stop this. And we'll now look at other examples. This is the end basically of my first example, and we'll look at 2 other examples that will actually show different capabilities of flow simulation, because this is only what I showed here is very just a short part of the capabilities of the software. I'll just close this. This example will actually show thermal analysis on a more complex system. We have a board with different electronic components, and we of course would like to see what will be the level of temperature reached on each and every different components, considering we have a fan pushing air in, and that the air will actually exit on this side here on the left side. So note also that we have defined a lot of different solid materials for all the components, because in this case, of course, we will consider heat conduction through the solid parts. So we have silicon, PCBs, steel, aluminum, and all that stuff, all that sort of materials. We define environment pressure conditions on these surfaces to make sure that, of course, air will come out by these spaces. Regarding the fan is actually the inlet of our system. In this case, we set a certain type of fan for which we were able to find, of course, the curve that will give us the behavior of the fan regarding the flow and the pressure differences for this type of fan specifically. So all these parameters are included in the software, but of course if the fan you need is not there, you can of course personalize this library and add up your own fan library. For each, well, I should say a few components, we also have power set values. So we have different power sets between 1 and 2 watts, for example. If I edit one, for example, so it's just a matter of selecting the 2 parts, entering the power value, and then you'll be good to go. Notice that you can also insert a power density or a constant temperature on this component. And we have two goals in this case, which is the maximum temperature evaluated on these two components here. So I'll just load up the results. It'll take a few seconds. And we'll look at what informations we're able to extract from this simulation. First of all, I'll just like to show a cut plot that will show us the temperature distribution of the air actually in the geometry. So we can see that where air is coming in, it's much more cooler in this section, and you can see the hot spots. Like this area here is much warmer than, of course, the rest of the geometry. Also, what you can do is actually show a surface plot. A surface plot will show you the temperature distribution on the selected components. So these components here, you can see exactly what is the temperature, and the heatsink here might be too warm. Well, actually, it's around 62 Celsius in this case. If I want more precise results, of course, I can probe at certain locations. So the heatsink is at 62. This chip here is at 48, this one is at 51, and 42 for this one. So you can see that this one at the back the flow is actually not going too much in that direction, so that's probably why it is so high. Same thing for the heatsink at the back there. All right, so I'm just hiding this now, and we'll focus on another feature. Once again, I'll show flow trajectories, and you'll be able to clearly see that the reason why it is so cool or so hot at some areas is because the flow is mostly going on this side, going over these components. So the components located in this area are, of course, cooler than the ones in this section, and there's a kind of vortex going just around here, this chip, so that's probably why it is much cooler than the heatsink itself. If I bring back the cut plot showing the temperature zone, you can see that indeed these sections here are much higher than the ones where the flows is going over the parts. So thermically speaking, we can create, of course, very, very good analysis and extract very valuable results that will, of course, help you during your design, thermically speaking. And lastly, another quick example of, in this case, an external analysis. We have here a space capsule entering atmosphere, for example, and we'd like to see how the flow is actually behaving. We used, in this case, a double symmetry because the geometry is pretty much the same in each direction, and we're looking at the Mach number now distribution for this space capsule re-entry, and we can clearly see the shock wave look because we're entering at Mach 1.7 in this case. So you see the shock wave distribution on the airflow created by this geometry. Note that we could also extract the goals. In this case, we add a goal regarding the drag coefficient. So the drag coefficient is actually evaluated by flow and given here through Excel of about 1.7 for this geometry at the speed given, of course, of Mach 1.7. So a lot of possibilities to extract informations that will, of course, help you to create better design with SolidWorks and with flow simulation. So this concludes the presentation I had for today. And if, of course, you have any kind of questions regarding flow simulation, it'll be my pleasure to answer these. So you can call me at SolidXperts if needed. And once again, my name is Jerome, and I'll be waiting for your questions if there's any. Thank you for your time, and hopefully we'll see you at our next presentation. Thank you, and have a nice day.